Hello everyone, welcome back to ACE IB. This is Stoichiometry Part 2. If you have not watched Part 1 yet, I recommend you watch that first before going and watching this video so that you have a good primer. I would like to start off with a quick lesson on naming compounds. Let's start with the ionic compounds because they are easier. For example, NaCl. This one is made up of Na and Cl, which is sodium and chlorine. However, as you might have guessed, the naming isn't just sodium chlorine. Instead, when we have an INE ending, we often change it to an IDE ending. So this compound, NaCl, is actually known as sodium chloride. This is true for most compounds that are ionic. For example, LiBr, which is lithium and bromine, is known as lithium bromide. Again, changing the INE ending of bromine into the IDE ending make it bromide. However, as you might know, some ionic compounds might be polyatomic, which means they might look something like this, NaNO3. Well, clearly this is not just going to be called sodium, nitrogen, oxygen, right? Nor will it be called sodium, nitrogen oxide or nitride oxide. Instead, NO3 is known as nitrate. That's NO3. So instead, this compound is just known simply as sodium nitrate, with no changes whatsoever to the second word of the compound. This is true for most polyatomics. For example, NH4OH, which the NH4 is known as ammonium, and OH is hydroxide. It's just known as ammonium hydroxide, and that's just the name. There's no changes if there's a polyatomic ion. However, if there's no polyatomic ion like we saw before, like NaCl or KCl, then the second word of the compound, which has an INE ending, will be changed to IDE. Covalent compound naming is slightly different from ionic naming. For example, look at these compounds. CH2, CH4, C2H4. With the ionic naming convention, all of these would be just called carbon hydride, but clearly they're not the same thing. So instead, when we have multiple of the same, we use prefixes in front of the element. The prefixes I will write on the right include mono, di, tri, tetra, penta, and so on. I'm not going to write the rest because they are rarely used. If there is one of the element for the first word, we don't put mono in front of it. So this one would simply be known as carbon dihydride instead of monocarbon dihydride. Can you guess what CH4 would be called? It's carbon tetrahydride. Pretty straightforward. What about C2H4? Well, it's not carbon tetrahydride because that's just CH4. So in this case, we add the di in front of carbon, and we get dicarbon tetrahydride. An example when we might use the mono prefix would be an element like CO. There is one carbon, so we just write carbon, and there's only one oxygen, but we don't say carbon oxide because that refers to all of the CO and however many O's there might be kind of compounds. So instead, this one is just called carbon monoxide. The one we're all familiar with, CO2, because there's two oxygens, is called carbon dioxide. Next, let's talk about the 6 types of reactions that are present in the IB chemistry course. The first one is called synthesis. In letter or algebraic notation, this is notated by A plus B yields AB. You can think of this as two elements coming together to form a compound. For example, C plus O is CO. Later on, we'll notice that this is not actually how things are formed, but for now, let's keep it that way for simplicity's sake. The second one is decomposition. You might have guessed by the word what it means. It means a compound AB splits into A plus B, two elements. It's basically the reverse of synthesis. Third type is single replacement. This one is notated by A plus BC yields B plus AC. This might look weird at first, but imagine A as an element and BC as a compound. A and B switch partners, so now B is by itself as an element and AC is the new compound formed. The fourth one is double replacement. It's similar to single replacement, except in this case, both of them find new partners. AB plus CD yields AD plus BC. It's very similar to single replacement, but instead of A being alone or B being alone, there's 4 compounds, so each of them will always have a partner. The fifth one I want to talk about is actually a special case of double replacement. This one is called neutralization. And neutralization is acid plus base yielding water plus salt. Now, it's important to note that this salt doesn't mean table salt. It doesn't mean sodium chloride NaCl table salt, but rather just any ionic compound. And we'll see why later on. When you have an acid and a base, they will always neutralize each other given that you have enough of each. And when they neutralize, they form a neutral substance, which is water. The last one is composition. Sorry, not composition, combustion. And this is basically combining an organic compound with oxygen, which will burn it, and it should form water, and carbon dioxide. I'm going to explain this one a bit later, and we will also see it a lot in the organic chemistry unit. Now, let's try some example questions. I will give you a reaction equation and try to figure out the type of reaction from the 6 aforementioned ones. Here's the first one. C plus O2 yields CO2. Second one. HCl plus NaOH yields water plus NaCl. 3. CH4 plus O2 yields H2O plus CO2. The first one is synthesis. It's carbon and oxygen coming together to form CO2, a compound. The second one you might notice that HCl is an acid and NaOH is a base. If you don't know what's an acid and what's a base yet, we will introduce that shortly, maybe in a next video or in a future video. But the short rundown is anything with an H in front is generally an acid, and anything that has an OH at the very end is a base. So we can say that this is an acid, and that's a base. And because when you have acid and base, they neutralize. They form water, and this is an ionic compound. And so this is neutralization. The last one here, CH4 plus O2 yields water plus carbon dioxide. So since we're combining something with oxygen here, and this is a hydrocarbon, which means it is organic, this must be a combustion reaction. Now I want to quickly go over balancing equations before we move on to actual stoichiometry. This is because balancing equations is very important, and if you don't know how to balance equations, then stoichiometry is not going to go well for you. Let's say we have this single replacement reaction, Mg plus HCl, and the products will be MgCl2 and H2. Why? Because Mg has a charge of positive 2. And so it needs two Cl's, which has a charge of negative 1, to make up for it and form a neutral compound with a charge of 0. You might notice, however, that there's one Mg here, there's one H here, and there's one Cl on the left side. On the right side, we still have one Mg, but we need two Cl's here and two H's. So we're missing an H and a Cl on the left side. What do? What if we just double this compound here that has both H's and Cl's? Now we have two H's and two Cl's, which means now the equation is balanced. We have one Mg, two H's, and two Cl's from Ng plus 2 HCl, and that yields MgCl2 plus H2, which we have one Mg, 2H, and 2 Cl on the right side. Please note that these numbers down here, like H2 and Cl2, these numbers cannot be changed, because by changing these numbers, you are essentially changing the compound that it is forming. You are only allowed to add whole number coefficients in the front of the compound, like here, where I specified that we are going to take two HCl's instead of one HCl compound for every Mg element that we have. Here is a slightly more complicated one for you to try. C4H8 plus O2 yields H2O plus CO2. Go ahead and pause the video for a moment to try it. Hint: balance O's last. Deal with the C's first and then the H's. I will review the solution in 3, 2, 1. Okay, so we have 4 C's on the left side, 8 H's, and 2 O's. Here we have 2 H's, 3 O's, and 1 C. Now, right off the bat, we can see that we have 4 C's here, and we only have 1 C on the right side. So we need at least 4 CO2 compounds. If we have 4 C's here, then now we have 2 times 4 O's, that's 8 O's, plus 1 O, that's 9 O's. So now we have 9 O's. However, notice on the left side, we only have 2 O's. Well, how can we deal with this? First of all, the H's aren't even balanced yet. So we have 8 H's on the left side and 2 H's on the right side. Therefore, we need at least 4 H2O's, which makes this 8 H's. 4 plus 8 O's, 12 O's, and 4 C's. Looking on the left side, we have enough C's and enough H's, but we only have 2 O's and we need 12. So we can put a 6 in front of this O2, which makes the number of O's on the left side 6 times 2 equals 12 O's. And this is the balanced equation. C4H8 plus 6O2 yields 4H2O plus 4CO2. The final concept I would like to introduce in this video is mole-mole stoichiometry. Yes, we are finally into actual stoichiometry. Let's say we have the following equation. N2 plus H2 yields NH3. The first thing you might notice is that this equation is not balanced. To balance it, we need to add a 3 in front of H2 and a 2 in front of NH3. And this is now the balanced equation. N2 plus 3H2 yields 2NH3. These whole number coefficients in front of the compound can be used as whole number multipliers or as ratios. Well, what do I mean by that? Suppose you had 18 moles of nitrogen. And we want to know how many moles of NH3 we can make. Well, stoichiometry says that we can take 18 moles of N2, multiply that by 2 moles of NH3 produced, because there's a 2 here, over every mole of N2 we put in. Because remember, if we don't write a number, that's just 1. And we should get 18 times 2 equals 36 moles of NH3 produced. This is what stoichiometry is all about. If you know how many of the reactants you have, you can predict how many of the product you will get, theoretically. The same is true for reverse. If I did this reaction and I got, let's say, 12 moles of NH3, then I know I must have started with 6 moles of nitrogen. Now let's try a hard question. A typical barbecue tank contains 103 moles of C3H8, and we have 103 moles of it. We want to combust this with oxygen, and we want to figure out how many moles of oxygen we need to completely react with and combust with the 103 moles of C3H8. Now remember, because this is a combustion reaction, the products will be water and carbon dioxide. And as usual, the first thing we need to do is balance the equation. This is the balanced equation. C3H8 plus 5O2 yields 3CO2 plus 4H2O. Now with these numbers and ratios, we can calculate how many moles of oxygen we need. We have 103 moles of C3H8, and we need 5 moles of oxygen per mole of C3H8 to combust it, as given here by the 1, invisible 1, and the 5. If we multiply these numbers, we get 515 moles of oxygen needed. Here is another question for you to try. How many moles of zinc phosphate are produced from 2.4 moles of hydrogen phosphate? So we have 2.4 moles of this. And my question is, how many moles of this one? You can pause the video here to try it out yourself. I will go over the question in 3, 2, 1. Okay, the first step is to balance the equation. We need 3 zincs, 2 hydrogen phosphates, 1 zinc phosphate, and 3 hydrogens on the right. This is now the balanced equation. I'm not going to read it out because it's a little bit too complicated and I'm kind of lazy. I'm sorry. We have 2.4 moles of H3PO4, and we form 1 mole, because there's an invisible 1 here, don't forget, of zinc phosphate, per 2 moles of hydrogen phosphate, we get 1.2 moles of zinc phosphate. And that is the answer, 1.2 moles. That's it for this video. We will go over mass, and volume, stoichiometry in the next video with solutions to follow soon after that. If you like what we're doing, make sure you like, subscribe, and we will see you next time.